So students, title of today's lecture is Coulomb, Blockade and Single Electron Transistor. So Coulomb blockade is a new concept for you, and the working of single electron transistor is based on Coulomb blockade effect. So first let's see what is single electron transistor, and after that we will try to understand what is this Coulomb blockade effect. Now a single electron transistor is similar to a normal transistor, but there are some special things in this single electron transistor. The one important thing is the channel is replaced by a small dot. You can see here. So this part, this island, this is a small dot, and this dot is replacing the channel. So there is a source here, there is a drain here, but this island, this small island is replacing the channel, and this dot is separated from source and drain by a thin insulator. So these portions which separates this island or this dot from source and drain, and they are separated with the help of a insulator. Now electron, when it travels from source, it has to tunnel in two steps. First, the electron will tunnel from source to drain, source to dot, sorry, and then from this dot to drain. So the tunneling will take place at two junctions. One junction is source to island, and second junction is this island to drain. So this is some special features of a single electron transistors which makes it different from a conventional MOSFET transistor. So we can define single electron transistor in this way. So it is a sensitive electronic device which is based on Coulomb blockade effect. So we will talk about Coulomb blockade effect in the coming slides. So it is called single electron transistor because the structure and the physics, or you can say the tunneling, is designed in such a way that normally at a time only one electron makes it possible to cross to this tunneling junction. So the electrons which are traveling from source to drain, they are traveling in a very controlled way, one by one. So you can say even the movement of it carriers are controlled at electron level. So the electron here in this device, they flow through a tunnel junction between source drain to a quantum dot, right? So it means a source to a quantum dot and then quantum dot to source, quantum dot to drain, sorry. Now moreover, the electrical potential of this island, so there is a electric potential barrier which avoids the movement of carrier from source to island and from island to drain. In normal transistor, conventional transistor, you can say there is a barrier in that structure also, and that barrier is modified with the help of gate voltage. So here also a barrier exists, and that is tunneling barrier, and it have electrical potential. So electron, if it want to cross from source to island, it must cross that potential barrier first, and this potential barrier of course can be tuned by a third electrode, which is the gate electrode here. So that is the third electrode which tunes this potential barrier, and this third terminal known as gate, just like conventional device, which is capacitively coupled to this island. So you can see here this capacitively coupled, it is the gate terminal is capacitively coupled to island. So but I told you that the working of the single electron transistor depends on Coulomb blockade effect. Remember, it is different from conventional transistor because channel is replaced by a dot, right, and this dot is separated from source and drain by thin insulator. So that way this dot, this portion is quantum confined because of the presence of insulating material on both sides towards source and drain. The carriers which are enclosed in this island, they cannot go easily to source side or drain side, right. So it is a like a case of 3D confinement, it is quantum dot. So let us now understand what is this quantum dot. So it is shown here. So for example, you can see here this small portion, this is a dot here, and these are leads, so through which current can pass, and this gap shows a type of isolation. Practically this isolation is implemented by placing here very thin insulating material layer, but here this insulation is shown in the form of free space. So this lead metal leads, they are separated from this dot structure. Now this dot is very small, and because it is very small, so the number of electrons which are placed in that dot is really very small. So this Coulomb blockade effect, it can be observed by making a device very small, just like this quantum dot, right, like a quantum dot. And you know what is this quantum dot? That is 3D confined structure. So in this 3D confined state, electrons inside this quantum dot will create a strong Coulomb repulsion. So normally in bulk bodies, there are large number of electrons present because of its big dimensions, and that way the presence of electrons that doesn't create much problem. But when the dimensions of this kind of dot are very small, only few number of electrons are present here. So no other kind of screening effect is present there. So whatever electrons are present here, they will create a field in this quantum dot, and the further movement of electrons from outside to dot or from dot to outside will become very difficult, because the electrons which are already present here, they have very strong repulsive force. They will not allow any fresh electron to come to this dot, right. And that way we can say that device will no longer follow Ohm's law. So Ohm's law says that if there is a potential difference, current should depend on that potential difference value, and if we increase the potential difference, current should increase. But this Coulomb blockade state says even if you increase the potential difference, current may not increase, because this dot will not allow new electrons to come to this place. So the reason it is mentioned here, this Coulomb blockade, because putting even one extra electron onto the dot would cost too much Coulomb energy, right. And this effect is known as Coulomb blockade, means bringing a unit charge even to this dot needs a lot of energy. The movement of electrons to this dot is restricted, and it is very difficult task now. So you know that from your 10+2 physics that the Coulomb energy is given by this expression. It says that this energy is dependent on the capacitance. So if you are trying to add, or if you are trying to bring an electron from outside to a particular plate of a capacitor, then you need this much energy. It is E square by 2c. Now what happens? So here this E is charged on the electron, and C is the total capacitance of source and drain junctions, right, or gate capacitor, whatever it is. So right now you just understand that this dot have certain capacitance. Now since we are trying to make this size as small as possible, now because of this small size, this capacitance also becomes very small, and because of that this EC, Coulomb energy, becomes very high. It means if you want to add an extra electron to this dot, you need excess amount of energy. And here you can see how the situation occurs. So this is the allowed energy state on the source side, and this is the allowed energy state on the drain side. The continuous energy states exist here, but because this quantum dot, it's because of this confinement, because of the strong confinement, quantum effects comes into picture, and the allowed energy states in this dot, they are discrete. In the leads, the allowed energy states are in the form of a continuous band, but in this quantum dot, because of this strong confinement, quantum effects are coming into picture, or you can say the allowed energy states are discrete energy states. So the electrons can exist only in this state or in this state, and this much is the Coulomb gap, you can say. So, if electron have to move from source to drain, it have to cross this gap, only then new electron will be added here. So, right now in this present situation, this state is filled state, right? This is filled state. The electrons exist in this state. So, we can call it, this is our filled state. I am writing here with the help of mouse. So, this is filled state and this is your empty state, right? This is filled state because, okay, just write here empty state. This is filled state because electrons can easily move from here to here. So, that is why this state is filled state. This is your source side, right? But this is your empty state because the electrons need higher energy. So, this much energy gap is there between allowed state, I mean filled state and empty state, and this is your Coulomb gap. And remember, this gap, Coulomb gap increases if the size of this dot decreases. If size decreases, this gap, Coulomb gap increases, right? This Coulomb gap increases if your size of quantum dot decreases. So, it means a large amount of energy need to be supplied if you want to move electron from source to this dot. So, the same situation is shown here. Now, two stable charge states of dot with n and n plus 1 electron are separated by Coulomb energy. So, this state is, suppose consider that n number of electrons are present here, and if we add one extra electron, then n plus 1 electron will go to this new state. So, this new electron, which I am denoting as plus 1, this new electron will go to this new state. But since there is a significant amount of energy gap, so the new electron must be provided this much energy, only then it will be placed in this higher allowed state. Now, dot capacitance decreases when shrinking the dot. It means when we are reducing the size, this capacitance decreases, and since this capacitance decreases, this forbidden gap increases further. Consequently, the Coulomb energy gap increases, right? So, I already explained this concept to you. And when this energy, so this is U is actually E, both are same thing. When this energy exceeds the thermal energy, then this single electron charging can be detected. It means normally what happens at room temperature, electrons have a thermal energy. Now, if this Coulomb energy is smaller than this thermal energy, there are possibility that electrons can move to this higher energy state, or you can say the adding of new electron to this quantum dot is not that much difficult. But at low temperature or for higher Coulomb energy, this possibility does not occur, right? Low temperature means if you reduce the temperature, this thermal energy reduces, and if this thermal energy becomes less than this Coulomb energy, then the problem starts, then this Coulomb blockade starts. Now, at room temperature, the electrons have about 25 million milli electron volt energy. This is thermal energy, right? And if we want this Coulomb energy to be greater than this energy, then the dimensions should be 10 nanometer, because our purpose here to create this Coulomb blockade is achieved when we increase this Coulomb energy beyond this thermal energy, and that is possible when the dimensions of the quantum dots are less than 10 nanometer. So, at that time this kind of Coulomb blockade is created, and this Coulomb blockade seems a problem, but that is an advantage here, because it gives us an opportunity that we can control movement of even a single electron. So, the current is controlled by the electron, by controlling the movement of electron directly. So, you can see here. So, if we plot the IV characteristics for this kind of quantum dot junction, that there is a quantum dot here, and then there are metal leads here, and this is your quantum dot. And because of this Coulomb blockade, if we want to add even a single electron here, even a single electron, if you want to add from this source to, this is source side, from source to this dot, then we have to supply energy at least equal to Coulomb energy. So you can see here that energy will be provided by applying a suitable potential. So that way that energy is quantized. So the energy which make electron to jump to this dot, that is quantized energy. You can see here. So only for a particular energy we feel current here in this system, because only for that particular energy one electron jump from this portion to this portion. So once the movement of electron is detected, we detect a current peak, and once this electron have moved to this new location, again further movement is stopped till we supply another big jump into the energy, right. So that way this energy, you can see the current peaks are discrete peaks. So at discrete voltage levels you get the current peaks. So from this second graph you can see here the number of electrons which are added into this quantum dot. So the number of atoms, for example, if there are n number of electrons are there in the quantum dot, now if we want to add one more electron here, we want to make number of electron n plus 1, then that happens only when a suitable voltage is applied, suitable extra energy is supplied to the electron here. So you see here how this single electron transistor is implemented. So this you have seen, this is your island, or you can say quantum dot. Now this is your quantum dot, this is your drain, and this side is your source. So since there is a insulating layer practically, and in the diagram I show you that there is a gap here, right, but practically it is implemented with the help of insulating layer. So because of the presence of that insulating layer, there is a capacitance here, that is left junction capacitance, and there is a right junction capacitance, which is capacitance between this island or quantum dot and drain, right. Now a gate terminal is also placed here, and that gate terminal introduces one capacitance, gate capacitance, right. Now the single electron transistor is composed of two tunnel junctions. This is one junction, this is second quantum tunnel junction, along with one island, which are capacitively coupled to two gate electrodes, sorry. So this island is capacitively coupled to this gate electrode, right. So this capacitance is shown here and gate voltage is shown here. This is gate voltage, right, and this is gate capacitance. So this island is coupled to source and drain with the help of these junction capacitances, and gate is also coupled with the help of this gate capacitance, right. So the island is located in between two tunnel junctions with capacitance CL and CR, which is shown here. Now this single electron transistor can electrostatically be controlled by this gate capacitance. Of course it is shown here, and the total capacitance of this island is now left side capacitance, right side capacitance plus gate capacitance, and thus such a setup is called a single electron transistor. Now whatever is the potential or energy needed to move an electron from source to drain through this island, that potential can be modulated or can be modified with the help of this gate capacitance or gate terminal. So you remember this EC was E square by 2C, and this here this C is replaced by C sigma. C sigma is the total capacitance. The total capacitance is gate capacitance, left side capacitance, right side tunnel junction capacitance. So since we are adding this gate terminal here, so this gate capacitance is being added here. So the total capacitance increases, and that way this capacitance has increased here because of introduction of gate, and that way the EC, this forbidden gap energy which is needed to move an electron from source to island, that energy decreases. So you can see here so this is your quantum dot, and these gaps, they are like some insulating materials are placed between source. This is source, this is drain, and this is your dot. So this is insulating material between source and dot, and this side, this is insulating material between dot and drain. So this is dot, right? Now this dot have quantized energy levels, you can see here, and they are separated by this energy gap. How much is this energy gap? That depends on its capacitance, or you can say its size. If you reduce the size, capacitance also reduces and this gap increases, right? Now when you are adding this kind of gate here, gate terminal here, and you are adding this gate capacitance, so what happens? So net capacitance here you can see is increasing, so this gap will decrease, or you can say that when you are applying some voltage on this gate terminal, so this bending of will be downward in such a way that the energy level, allowed energy levels in this quantum dot, they will be pulled in the downward direction, and for a certain voltage it will be aligned in such a way that the electron can easily move from source to drain. So it is possible because we are applying a suitable voltage here on this on the gate terminal, right? So that way the movement of electron from source to drain is allowed here, but remember this movement is in term of a single electron. So what are advantages of these kind of things? So first you should remember that the size of this quantum dot is very small, so it's possible to make it very compact, and that is our basic aim in the microelectronics, or you can say in the nanoelectronics. We want to make the electronic systems very small, right? Now of course high operating speed it will allow because its dimensions are very small, and it's very sensitive. Small voltage fluctuation that will make electron to move from source to dot and dot to drain, right? And it will consume very less amount of energy, because here the amount of current which is passing, that is in term of single electron, and that is controlled with the help of gate voltage, and gate will not have any current there, right? So the single electrons are moving, so it will consume very less amount of energy. Now another big advantage of this, straightforward co-integration with the traditional CMOS circuits. So whatever CMOS circuits we have right now in the electronic systems or in the integrated circuits, so this kind of single electron transistor can be integrated with the existing CMOS circuits, or you can say the existing CMOS circuits can be implemented with the help of single electron transistors, or you can say single electron transistors can replace your conventional MOS devices. So I hope that now you understand what is a single electron transistor. You understand what is this Coulomb blockade effect. If you have any doubt still, you can discuss with me. Thank you very much.